Let's take a look at the math of Newton's law of universal gravitation. We have an equation called Newton's law of universal gravitation. A synonym for the force of gravity is weight. But more importantly, this is the force of gravity that is an attractive force between all matter. Anything that has mass will exert a force of gravity and attraction on another mass. So for instance, if I have two masses, here's mass 1, and here's mass 2, these things will be attracted together by a force that depends on how big the masses are, m1 and m2, how big the distance is from their centers, so it's very important, this is always measured from the center of the object, and a constant called big G. And big G is a very small number. It's 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. So what you can see, this number is so small that if we calculated how much force would exist between two 1 kilogram masses separated by a distance of 1 meter, we would get the very, very small number of 6.67 times 10 to the negative 11 newtons. Be very, very difficult to detect. Now, using this formula is simply a matter of having all the information except for one of the variables, solving it for that variable, and plugging in the numbers. It's important to notice that the distance is squared in this formula. One of the consequences of that is that the force of gravity falls off with distance very rapidly. If I double the distance between two objects, I will have 1/4 the force. If I triple the distance, I'll have 1/9 of the force. Now, you're going to be asked to do a lot of questions that compare situations where we do change one of these variables. So what I'm talking about would be a situation where we said something like, if we had two objects that had a force of, say, 10 newtons between them, and we doubled one of the masses, what would happen to the force? Now, I have a method that I've developed over the years that makes this pretty easy. What you do is you take every number in the right side of this equation that doesn't change and you replace it with a 1. And then you take the one that does change and you replace that with what you're doing. So for instance, if I'm going to double one of the masses, I'd turn the G into a 1. And I would double one of the masses, keep the other the same. The only thing that changed was the mass that doubled. So what we wind up with when it's all said and done is a 2, which means that that would double that force, which would make this 20 newtons now. Another example could be, what happens if I cut the distance by 1/3? So again, I would replace everything that didn't change with a 1, and then perform the operations on what's left over. And what I would have is 1/1/9, which becomes a 9, which means my force then will be 9 times greater if I cut the distance by 1/3. What if we doubled one of the masses and tripled the distance between them? You can change more than 1. So I would double one of the masses, triple the distance between them, which means I would have 2/9 as much force as I had before. There's an extension of this, which is what happens when you look at the way we used to look at weight, which is that weight was mass times G. And we've always thought of this G as being the acceleration that an object has when it's in free fall due to gravity. There's another way of thinking about this, and the way we think about this in this chapter is that we call this the gravity field strength. All objects that have mass create a field around them called the gravity field. And if you place another mass in that field, it will experience a force. This is how we kind of explain the fact that objects are able to exert forces on each other when they're not touching. Let's say, imagine I have a planet. MP stands for mass of planet. And I have an object sitting on the surface of that planet. And I'll call that mass of object. And there is a distance between their two centers, r, and I want to know how much that object weighs on that planet. Well, the force of gravity would be big G, mass of the planet, times the mass of the object over the radius of that planet squared. Now, of course, this is if we were sitting just on the surface. If I pull the mass of the object out front, and rearrange it a little bit, this force that we're talking about is the weight of the object, and that would be the mass of the object times g. Well, everything in these parentheses is what determines what g is on this planet. So for instance, if I took g, and I'm making a new formula here, that this is the mass over r squared. And by the way, it doesn't have to be a planet. This is a general equation that could tell you how big g is out here, or anywhere in the vicinity of this large body. So this g is the mass of that body, and then the r is the distance away from the center of it. Now, if I were to put the numbers in here for the planet Earth, I'm going to skip the units on big G for now. The mass of the Earth is 5.98 times 10 to the 24 kilograms. The radius of the Earth is about 6.38 times 10 to the 6 meters. If I put these numbers in here and do the math, I come out with, well, hallelujah, look at that. This is where the 9.8 comes from. It has to do with the mass of the Earth and the size of the Earth. This is a formula that you can also use in a very similar way to use the big Newton formula. You can do things like say, well, what would happen to the size of G if I double the mass of this planet, or if I cut its radius in half, or if I doubled its mass and doubled its radius, that kind of thing. And you can perform the same kind of operations on it that you did on the other one.